Open the GIS app project from the GIS app folder you copied from the DVD. This is the Yellowstone area we worked with in the Getting Started with VNS2 tutorials. The goal of these tutorials is to use real-world shapefiles and their attributes to place lakes, streams, roads, and ecosystems with search queries and thematic maps. If you haven't finished the Getting Started tutorials, please do so. These advanced tutorials assume you've completed the introductory material. Before starting with lakes, let's get familiar with the GIS app project. Open the database editor. We're working with 10-meter DEMS. The only vectors we have are the quad boundaries that VNS created when the terrain data was imported. Open the component library and let's see what else we have in the project. Component categories are listed with inset components if they exist. Double-click the Atmosphere's Haze component to open its editor. This is the default VNS Atmosphere component. Close the editor when you're done. We have 15 cameras. The Plan Default camera is open in the upper right view, and the Geyser Basin Perspective camera is open in the upper left view. The coordinate system is UTM NAD27. The plus sign in front of it indicates that active objects are attached, in this case, DEMS. We have no ecosystems yet, and the environment is the VNS default. The Yellowstone NP ground effect is a modified version of the ground effect we built in the Getting Started tutorials. Open its editor and go to the Material, Gradient, and Driver page. A new material, Hydrothermal Deposits, has been added to the low slope end of the gradient. Close the editor. Render a geyser basin preview. The Hydrothermal Deposits material renders a large white and tan fractal noise texture on flat terrain. The shapefiles we'll use were downloaded from the Wyoming Natural Resources Data Clearinghouse at the University of Wyoming Spatial Data and Visualization Center. The data is from the Yellowstone North 1 to 100,000 theme section. For convenience, these files have been uncompressed and included in the Data folder on the DVD. Except for the lakes and land cover shapefiles, this data is as it came off the WNR server. Before we import the shapefiles, we need to know more about them. Go to the Data folder on the DVD and open the hydro100k.met metadata file in WordPad or Simple Text on a Mac. To accurately place the data on the terrain, we need to know its coordinate system. Go to the Spatial Reference Information section. This defines the horizontal coordinate system. The coordinate system is geographic and uses the North American datum of 1983. Next on our information checklist are shapefile attributes. Find the Entity and Attribute Information section. For now, we'll just consider attributes as they relate to lakes or polygon features. The major attributes designate who digitized the vectors, which is not important to our project. The minor attributes are the ones we're looking for. Minor 1 is the code for feature type, given lower down in the polygon attribute value list. For example, 111 is a marsh wetland. 412 is a wide river represented by left and right bank, and 421 is a lake or pond. Most features only have the minor 1 attribute. If the minor 2 value is non-zero, it's usually 610, indicating an intermittent feature. We'll use this attribute to control whether or not water fills our lake beds. The third attribute we'll use, ELEV, is the elevation of the lake's surface in meters. It isn't included in the WNR metadata because I added it to the shapefile. Open a second VNS application window. Let's do a test import in a clean project to check the import settings and see what other attributes we have in the shapefile. Create a new project and name it Test. When the Import Data box opens, select Yes to import data. Go to the DVD Data folder and load lakes.shp. The import wizard will open and correctly identify the file as a shapefile. Go to the next window. The Load As window correctly selects a vector object for import, so continue to the next window. We'll use one of the shapefile attributes to name the vectors, so go to the next window. The Coordinate System Editor opens because the import wizard was unable to identify the coordinate system from the data itself. The metadata identified the shapefile coordinate system as geographic NAD83. Go to the System page and select Geographic NAD83 from the System drop-down list. Close the editor. The Coordinate System Summary will update with the Geographic NAD83 information. Go to the next window. Shape Options lists the shapefile attributes and offers options for using them. This is an import test, so we'll go with the defaults. Use the shapefile to attach layers, assign database names, and load attributes. Import the shapefile. We added a new coordinate system, so VNS wants to know if it should become the new default. We won't be doing anything special with this project, so go with the default Yes answer. The first Database Fields window lets us select the shapefile fields to load as object attributes. Multiple select the minor 2, minor 1, and ELEV fields, and click OK. The next Database Fields window is looking for database layers. It's a good idea to group similar features by layer, so select minor 1. Recall that this code designates the type of polygon feature, for example, lake, marsh, or wide river. Click OK. The last Database Fields window is looking for a name field. The hydro50_ID sounds promising, so select it and click OK. Open the database editor. The shapefile imported as 255 objects. Select the first object, 20, and turn to its attributes page. This object has a minor 1 code only. The layer page lists the minor 1 attribute we loaded as a layer name. Let's see if the hydro50ID was a good choice for a unique object name. Select the Search button at the bottom of the objects list. The Input Request box search string is already filled in with the name we selected in the object list. That's what we want, so OK or Enter to search the list for objects named 20. The database title bar shows 5 objects found, so I guess that wasn't a good choice for a unique identifier. Close out the test project and return to GIS app. Armed with the new information the test import gained us, launch the import wizard. Go to the DVD Data folder and load lakes.shp. The wizard will open and correctly identify the file as a shapefile. Go to the next window. The Load As window correctly selects a vector object for import, so continue to the next window. Since we didn't find any unique identifier fields in the test import, let's name this one ourselves. Change the name to Lake and go to the next window. Go to the Coordinate System Editor System page. Select Geographic NAD 83 from the drop-down list. Close the editor. When the Coordinate System Summary updates with the Geographic NAD 83 information, go to the next window. In Shape Options, we'll use the shapefile to attach layers and load attributes only. Deselect Assign DB Names from an attribute field. Import the shapefile. We've added a new coordinate system, so we're asked if we want to make it the default. I prefer to work in the DEM coordinate system, so click No. The first Database Fields window wants attribute fields. Multiple select the minor 2, minor 1, and elev fields, and click OK. The next Database Fields window is looking for database layers. Select minor 1 and OK. Select the Lake 255 vector at the top of the objects list. The database editor will add the 255 new lake objects to the existing 75 for a total of 330. The plan default view will refresh with new vector objects. Go to the Layer page. Let's organize the lake vectors using feature type rather than feature code. Revisit the minor 1 code list in the metadata. 111 is marsh wetland, 412 is wide river, and 421 is lake or pond. Select the 412 layer and click the Layer Select button. 12 vectors will be selected. Add a layer and name it Wide River. Select Lake 100, one of the 421 vectors, and Layer Select. 421 is the lake or pond code, so add a layer and name it Lake. Select Lake 3, one of the 111 vectors, and Layer Select. 111 is marsh or wetland, so add a layer and name it Marsh. Select Lake 6, one of the remaining lake vectors, and Layer Select. It has a minor 1 code of 0. This doesn't do us much good, so we'll just leave them on the 0 layer. Save the project as GIS APP 1. The vectors were imported at their shapefile elevations. Select Edit to open one of the selected vector editors. Turn to the Selected Points page and you'll see an elevation of 0 meters in the lower right corner. Close the editor. Open the Geyser Plan camera in the upper right view. Planimetric views are designed to show vectors regardless of elevation. Switch the Geyser Basin view back to real-time mode. Perspective views only show vectors between the terrain and camera, so we don't see them in the Geyser Basin view. To quickly select all lake vectors, click the Object Search button in the database editor. Remove the number after lake in the search string field and search. All the lake objects are selected, which we can confirm with the 255 of 330 message in the editor title bar. Go to the Extent page and conform to terrain. Confirm the operation. VNS will confirm that all selected objects have been conformed to the terrain. Save the project. The geyser basin view will refresh with the conformed vectors. Let's change the real-time vector color to make it easier to identify lake features. Go back to the Layer page in the Database Editor. The last selected object is on the Wide River layer, so Layer Select. Go to the Properties page and slide the red and blue color sliders all the way to the right. Go back to the Layer page. Select the Lake 100 vector, which is a lake, and Layer Select. Go to the Properties page and change the render color to 0 red, 0 green, and 255 blue. Go back to the Layer page. Select the Lake 16 vector, which is a marsh, and Layer Select. Turn to the Properties page and change the render color to 0 red, 255 green, and 0 blue. Save the project. Refresh the views from the icon toolbar. Let's fill some lakes. Go to the Water Task mode and add a generic lake component. Notice that the resolution is 90 meters. Go to the Database Editor and slide down to the YNP-100M DEM. It's disabled, but the lake resolution is still grabbing it. Reset the lake resolution. The first thing we'll do is tell the lake component where to place lakes. We'll use the imported lake vectors from the database, so go down to the Vector Placement section and add a new search query. The search query defaults to all objects, which will work just fine. Go to the Selected Filter page. Here's where we set up the criteria for the search query. We'll use a vector attribute to select vectors, so go down to the Attribute field drop-down list. Choose Minor 1. It's the attribute for feature type. The minor 1 value for lake polygons is 421. Check the equals box and enter 421 in the value field and enter. Let's check the search query. Go to the Database Editor and open the Attribute tab. Go to the Search Query General page and select Items Now in the lower right corner. If the search query is set up correctly, the Database Editor will show 164 objects selected with the minor 1 attribute of 421. So far, the search query finds all lake vectors. That includes lakes with a minor 2 attribute value of 610, indicating an intermittent lake. We don't want intermittent lakes to render as lakes with water, so add another filter. This one is going to subtract objects from the first filter group, so select Subtract Objects. Go to the Selected Filter page. Expand the Attribute field drop-down list and select Minor 2. Check the equals box, enter 610 in the value field, and enter. Go back to the General page. The first filter will add all objects where the minor 1 attribute is equal to 421. The second filter will subtract those 421 objects where the minor 2 attribute is 610. This will leave us with non-intermittent lakes. To test the revised search query, select Items Now. The database editor now shows only 150 objects selected. We're not quite done. Although the metadata indicates that a minor 2 value of 610 is the most common, it did not say that it was the only option. Since we don't know what other minor 2 values there are, we will subtract all non-zero minor 2 lakes. Confirm that the second subtract filter is active on the general page, and go to the selected filter page. Make the attribute field not equal to 0. Go back to the general page. The second filter will now subtract those 421 objects where the minor 2 attribute is not equal to 0. This will leave us only lakes that have no supplemental minor 2 attribute. Click Select Items Now to test the revised search query. Save the project. The database editor now shows only 146 objects selected. Now the lake search query is ready. Close the query. The lake component will now place lakes within all minor 1 421 lake vectors. Now we'll specify an elevation for the lake surface, currently at its default value of 0 meters. We can't use a static value because the lakes have different elevations. That's the reason the elev attribute was added to the shapefile before import. Knowing what you need to do with imported shapefiles can often help you modify them before import. We'll use a thematic map to map the lake vector elev attribute to the lake component elevation. Click the Thematic Operations button to the right of the elevation field and create Thematic Map. Rename the Thematic Map Lake Elevation to make it specific to the lake component. The Database Linkage section tells the Thematic Map which database objects to use. We're just interested in the lake vectors, so go down to the Dynamic Link drop-down list and select the Lake search query. Go to the Data page. Here we choose which attribute to map to the lake elevation. We're only using a single value, so leave single value checked and choose ELEV from the Mapped Attribute drop-down list. Save the project and close the Thematic Map editor. Render a geyser basin preview. You'll probably get an error initializing effects. That's because the lake component has added 255 vectors to the render equation, although most of them are outside the DEM bounds. VNS evaluates each vector over terrain at a resolution of 10 meters, which takes quite a bit of memory for 552 square kilometers. Open the component library and increase the maximum effect memory to 300 megabytes. There may be a magic formula for figuring out how much memory you need, but I just increase it until the preview renders. It's okay to allocate more than you need. VNS won't use it unless it has to. Save the project. Open the status log from the animation toolbar. We save the project and start a preview render. Lake memory was allocated, but there wasn't enough for Thematic Map memory, so 0 was logged and we received an error. We just increased the maximum effects memory and save the project. Start another preview render. This time there is enough for both lake memory and Thematic Map memory, about 282 megabytes combined. Close the status log. The preview render does not show water in the foreground lakes. Open the diagnostic data window if it isn't open, and click within the lake vectors. the lake component rendered there, and the terrain elevation is about 2200.66 meters. Switch to a real-time view and retain diagnostic data. Alt-click the left lake vector and open the attribute page. The ELEV value is 2200 meters, about 0.66 meters below the terrain. Switch back to the preview render. We're seeing lake component beach rendered in the preview because the terrain is slightly higher than the water elevation. The 10-meter terrain doesn't have the detail we need to properly render these small lakes. No problem, we'll just dig out the lake beds we need. Go to the Terrain Task mode and add a generic Area Terraffector. Reset the resolution and rename it Lake. We can use the Lake search query to select lake vectors from the database. Go to the Vector Placement section and choose the Lake search query from the Dynamic Link drop-down list. Go to the Elevation and Roughness page. Leave the elevation relative to the vector and enter -3 into the elevation field. This will carve out the lake area terrafector 3 meters below the vector elevation. Return to the General page. Check Use Profile and Edit Profile. The default profile has the lake area terrafector reaching its 3-meter drop 10 meters in from the vector. This will work nicely for the lakes, so keep it. Open the status log and clear the list. Save the project and render a preview. The addition of the lake area terrafector has increased the effects memory by 58 megabytes and put us over the 300 megabytes allocated. Bring the component library forward and increase the maximum effect memory to 400 megabytes. Save the project and render a preview. We now have lakes with water in them thanks to the lake area terrafector. The status log shows a total effects memory of about 340 megabytes. The geyser basin preview shows an edge problem. Let's zoom in on the left lake. Open the Goose Lake camera in the upper left view and render a preview. Bring the Area Terrafector editor forward and check high-res edges. This often smooths edges without memory cost. Clear the status log and save the project. Open the Goose Lake camera in the upper right view and render a preview. It didn't take any more memory, but it didn't make any difference in the render either. Rough edges sometimes occur when effect resolution is too high. It's usually not the first fix we try because it's costly in terms of additional effects memory. Drop the effect resolution to 5 meters. Bring the component library forward and increase maximum effect memory to 1000 megabytes. Render a preview. The increase in effect resolution increased area terrafector memory from 58 megabytes to nearly 232 megabytes. Unfortunately, it did not improve the lake area terrafector edge quality. Bring the Area Terrafector editor forward and reset the effects resolution to its floating value. We've eliminated common settings within VNS as the cause of the rough edges. That means it's probably a vector resolution problem. We don't have enough points in the polygon to give us a clean edge. Open the Goose Lake plan camera in the upper right view. Save the project and render a preview. Use the Measure Distance tool to measure the southeast-northwest extent of Goose Lake, the one on the left. The length of the lake is about 600 meters. Switch back to a real-time view, retaining diagnostic data. Activate the vector and show points. The southwest shore of the lake has no more than 20 points over a 600-meter distance. On average, that's about one vertex every 30 meters, give or take. For clean edges, I like to have at least one vertex per terrain grid, in this case, one vertex every 10 meters. That means we need to increase the point count in this polygon by a factor of 4. Double-click the vector in the plan view to open its vector editor. Go to the Point Operations page and change the number of points to 200. Click the Change Now button. The real-time view will refresh with the new points. Open the Goose Lake camera in the upper right view. Save the project and render a preview. More points doesn't take any more memory and cleans up the edges of the lake. The downside is that you have to increase point count on a vector-by-vector basis. This is a common problem with imported vectors and shapefiles. They were usually not created for detailed visualization, so point count and smoothness is lacking. Bring the database editor forward. Search objects for lake vectors. Uncheck the Render checkbox. Open the Geyser Basin camera in the upper left view. Save the project and render a preview.